Alright guys, so this video will be about standing waves, which is the next wave phenomena that we're going to look at. And the thing about standing waves is that they're a result of the interference of two waves traveling in opposite directions from each other. So these will occur when, say, we have a string fastened to both ends. So you can kind of think of a guitar string where it's one part is fastened to the guitar, the other part is, kind of fastened to the peg. And so both parts are kind of held in place. The string can't vibrate on those two ends. And then you pluck it, and it's going to create a standing wave. This also occurs in columns of air. So a tube that's open on one end and kind of capped on the other, or even tubes that are open on both ends, these standing waves can result. And they are formed when we have two waves traveling in opposite directions through a string or through a column of air, or really through any medium. Okay. Now, when they do this, they overlap with each other and they will superimpose. And so some of these areas, they'll superimpose, and like a crest will meet a crest or a trough will meet a trough, and they'll reinforce each other, and that's called constructive interference. And in those areas, they will cause these very large vibrations, which we call antinodes. Now, in other areas, they're going to cancel each other out. So when they cancel each other out, they will form a node. So they will, like say, a crest and a trough will meet. And when they do that, they're going to cancel each other out. And so this region at the node won't vibrate up and down. They're called standing waves because it does look kind of like you have one wave that are just, kind of standing in place. But again, I want to emphasize that there's actually many waves traveling back and forth on the string, and they interfere with each other as they travel back and forth. Now, only certain wavelengths and certain frequencies will be able to create standing waves in a string or in a column of air. So what we're going to look at in this video is how do we determine what wavelengths, and therefore, through that speed equation, what frequencies will be able to create standing waves in a certain length of string or in a certain length of tube. So we're going to kind of look at three systems here. Okay, so you imagine we have a string and it's got a certain length L, and we think of the kind of the wavelengths that can fit. We say that can kind of fit in this length L. So the restriction we have in this is that, let's see if I can change my color here. So the restriction that we have is that we have to have a node on each side. Okay, so because this string can't move where it's attached, only wavelengths and frequencies that will allow the node to exist on the two ends will be able to kind of fit in this length. So when we look at this, we can kind of see this, like this is a whole wavelength. So there's a crest, a trough, and then back up. So in this case, the length of the string is equal to the wavelength of the wave that fits in there. Now this, it just goes kind of up from a crest and then down, and this is only this is like half of a wavelength, okay? So we would say that the length of that string is only 1/2 of the wavelength of the wave that's vibrating back and forth. Here, we can see that the length is equal to a whole wavelength plus another half. So we would say it's equal to 3/2 of a wavelength. We start to notice a pattern here. This is called our fundamental, or the first harmonic. And so we give each of these n numbers. And so this first one represents the lowest frequency, or the longest wavelength that can fit in this length. Okay, so this is the largest wavelength, their lowest frequency that can fit. And we say that that's n equals 1, or the first harmonic. The second harmonic we call n equals 2, okay, which has twice the frequency, or half the wavelength of the first harmonic or fundamental. And then we have n equals 3. And so if you notice, we have a 1 here. Now you can think of this as kind of like 2 over 2. We have a 3 here. And so we have a general equation here that for a standing wave in a string, the length is going to be equal to whatever the n number is divided by 2. Kind of took that away there. Divided by 2. Divided by, times the wavelength of that wave. So if we know the length that we have, the length of the string, and we know the harmonic number, that we're looking at, we can calculate the wavelength that would have, or vice versa. You know, if we know what the length is, if we know what the wavelength is that we want to create a standing wave, we can calculate the length that we would need as well. Okay, so that's the equation for standing waves in strings. But as I said, these standing waves can also be created in tubes. So one type of tube has a closed end, and so in this one we have to have a node. Okay, so that's kind of the restriction we have here. We have to have a node on the capped end. So whatever wavelength we have, whatever frequency we have, it has to be so that there's a node and that there's destructive interference at the capped end. Then at the other end, we have to have our antinode. Okay, so there has to be destructive interference because this is going to be open. Okay, this is going to be open. And so these are the waves that we can produce here. Now, if you look at this length is going to be 1/4 of a wavelength. Okay, so it's going from kind of equilibrium up to the crest, and this is only going to be equal to 1/4 of the wavelength. So this length is only 1/4 of this whole wavelength. This one, the length, will be equal to, here's a half and then a quarter. So this will be 3/4 of a wavelength. And then finally here, we have a full wavelength plus a quarter. And so this will be 5/4 of a wavelength. Now going back to our end numbers, this would still be our fundamental. But notice that the second harmonic doesn't fit in here. Okay, the next wavelength that could possibly fit in here is going to be 1/3 of what it was here. Or you can think of it this way, that the frequency that fits in here is going to be 3 times, the frequency that fits here is going to be 3 times the frequency that fits here. So what we have in a standing wave in a closed tube is we can't get every harmonic in there. Okay, for these, we can only get odd number harmonics allowed. Okay, so only, I should emphasize, only odd number harmonics allowed. So with the strings, we could have, you know, everything. We could have even, we could have odd, whereas with a closed tube, only the odd number harmonics are allowed. And then we get the equation, you can kind of see it here, you know, it goes 1, 3, 5. So it's going to be n divided by 4 times the wavelength, where n can be an odd number. So 1, 3, 5, so on and so forth. Okay, so that's the equation for a closed tube, a tube closed on one end and open on the other. If you ever blown across the mouth of like a pop bottle and you hear it whistling, this is what you're doing. You're causing a standing wave to be formed, and this would be the top of the pop bottle. This is where the liquid is. Okay, so you set up a standing wave, and then as you drink it, you'll notice that the pitch gets lower and lower because this length gets longer and longer and longer, which means that your wavelength gets larger, which means that your frequency will get smaller and smaller, and so your pitch actually drops down when you do that. Okay, and then finally, we have standing waves in an open tube. So an open tube would be a tube that is not capped. It's open on both ends. And so with this one, the length that we have, so here we have to have an antinode on both ends. So let's make note of that. We have to have an antinode here, and we have to have an antinode here. Okay, so there has to be constructive interference on the end. And it turns out that this length, so going from a crest down to a trough, is 1/2 the total wavelength. So the length of the tube is 1/2 the wavelength of the standing wave that exists. Here, we can see that the length is going to be equal from a crest down up to a crest. That's the whole wavelength. So here, length is equal to a wavelength. I mean, you know, we can think of that as 2 out of 2 wavelengths. And then here, we have 1 wavelength plus 1/2 a wavelength. So here the wavelength is going to be equal to, it's going to be equal to 3/2 of wavelength. And we get the same progression that we had with strings, where our equation, the length of an open tube is going to be n over 2 times the wavelength, and n can be any whole number. So once again, for an open tube, we can have both even and odd number harmonics set up in these tubes. Now, a cool application of this is with instruments. So you'll notice that some instruments behave like closed tubes, where there's a kind of a cap on one end and then it's open on the other end. I believe, very often flutes are like this. And so the flute sounds like a flute because of the harmonics that are in it. And notice that, you can have the fundamental, but you can also have harmonics at the same time, but you can only have the odd number harmonics. Whereas something else, like a trumpet or a saxophone, behaves like, let me get back here. Okay, behaves much more like this open tube where you have antinodes, and so it sounds different because it has different harmonics as you're playing it at the same time. So we can talk more about this in class, and we'll do some practice with these calculations. Okay, and if you have any questions, please let me know.